We're going to be talking about half-life. Half-life is the rate at which radioisotopes decay over time. Remember that radioisotopes are unstable isotopes that go through either alpha or beta decay in order to become or gain stability in the nucleus. So here's a couple graphical images of what half-life looks like. Half-life is the time required for 1/2 of a parent radioisotope, that's the original sample, to decay into the daughter isotope, which is the product of the decay. So a parent isotope starts off at a certain quantity and over time it decays by half. If you can see in the graph, the bar graph on the left, you have the half-life of iodine-131 and it turns into xenon-131. The iodine-131 is represented by the blue and the xenon, or the daughter isotope, is represented by the orange. So you start off with 100% of iodine-131. After one half-life, you now have half iodine-131 and half xenon-131. In the third bar, you now have a 25-75. And in the fourth bar, you have a 12.5% iodine-131 to 87.5% xenon-131. So it reduces by half each time. In the graphic on the right, this is what it looks like on a scatter plot, which is an exponential decay curve. So on the x-axis, you have the number of half-lives. And in this isotope's half-life, it equals 29 years, which means that every 29 years, half of the parent isotope will decay into the daughter isotope. So for this one, we're dealing with strontium-90, and you start off at the very top on the y-axis at 100%. After 29 years, which is one half-life, if you look on the x-axis, you now have 50% strontium-90 and 50% of the daughter isotope. And in this case, that went from 10 to 5 grams. After another 29 years, you now have only 2.5 grams, and after another 29 years, you now only have 1.25 grams, and then you can expect on the fourth half-life, you would have half of that 1.25. The rest of the 10-gram sample is now the daughter isotope. Every single half-life is unique to each radioisotope. Here are a couple of examples that I'd like you to jot down. Carbon-14 is a very important isotope for dating life within the past 60,000 years. And carbon-14 has a half-life of 5,730 years. That means if I have a 10-gram sample of carbon-14, 5,730 years later, I will only have 5 grams of that sample, and the other 5 grams is now the daughter isotope, which in carbon-14's case is nitrogen-14. Uranium-238 has an extremely long half-life. It's basically 4.5 billion years, and that is equivalent to the age of the Earth and our solar system. Iron-60 has a half-life that's kind of in the middle. It's millions of years, or MYA. It has a half-life of about 1.5 million years, which is still equally long, but if you are a scientist and you want to know something that deals with the age of the Earth, uranium-238 is going to be the isotope that you want to use, not iron-60. Iron-60 just isn't long enough of a half-life. Each isotope serves a different purpose. If you're a scientist and you want to look at the past 100,000 years of Earth's history, the past 20 million years of Earth's history, or the past 4.5 billion years of Earth's history, you need a different isotope to do that. All right, so I'm going to show you how to calculate half-life, and the equation on the right-hand side says that the amount remaining after a certain amount of half-lives have occurred equals the initial amount of the sample times 1/2 to the power of little t divided by big T. And I'll explain what each of those variables means. So that's the equation that we're going to be using. And if you look on the left, the graphic says the number of half-lives, so it goes to 1, 2, 3, 4. And this pertains to the mass left, which is also equivalent to the amount remaining. So the purpose of looking at this graphical is I want to show you numerically what a half-life looks like. So in the first half-life, you take that half and the denominator is to the power of 1, which means that 1 half-life has occurred. And so that means you've lost 50% of your mass sample, whatever that value is for m. After 2 half-lives, it's 1 divided by 2 to the second power, which is equivalent to 1/4, which means you have 25% remaining. To the third half-life, you have 1 over 2 to the third, which is equivalent to 1/8. And then on the fourth half-life, you have 1 divided by 2 to the fourth power, which is equivalent to 1/16 the mass remaining. So that's kind of a visual way to see how much remains after each half-life, regardless of the sample. It's always going to be reduced in half like that. So that leads us into our first calculation. Iron 59 is a commonly used isotope in medicine. So what they use iron 59 for is to diagnose blood circulation disorders. So they will inject a patient with iron 59 and they will watch what happens to the radioactive sample in their blood over time. The half-life of iron 59 is pretty short, 44.5 days. So that means that every 44.5 days, half of that iron 59 sample turns into its daughter isotope. So the question says, how much of a 2 milligram sample will remain after 133.5 days? So this is what we know. It's important to list out what you know so you know what you're finding. We know the initial amount of the sample is 2 milligrams. We know that the time elapsed is 133.5 days, which is little t in that equation from the last slide. And then the half-life is 44.5 days, which represents that large T from the equation from the last page. What are we looking for? The amount remaining. And the amount remaining is going to be in milligrams because the initial amount was in milligrams, so that unit carries over. So let's look at this question in terms of that equation. So the equation is the amount remaining is equal to the initial amount of the sample times 1/2 to the power of little t divided by big T. So what I have here is all of the variables that we were given plugged into this equation. So the amount remaining is what we're solving for. The initial amount is 2 milligrams. The elapsed time is little t, and it is 133.5 days. The half-life of this sample is 44.5 days, which is the big T. So, how much is remaining after 133.5 days? Well, the first step is to solve for this right here. So little t divided by big T, and that's going to get us our exponent. So our little t divided by big T is 133.5 days, that's the time elapsed, divided by the half-life of the sample, which is 44.5 days. And you notice these units are going to cancel out, which means that your answer has no units, or it's unitless. So this tells me right here, if you take 133.5 divided by 4.5, it's going to get you the number 3. Like that. This value tells you how many half-lives have passed since the original sample was given to the patient. So 3 half-lives have happened. And if you write that as a fraction, it's going to be 1 over 2 to the third, which is equivalent to 1/8. If you're not a big fan of fractions, 1/8 is simply 0.125. So after 3 half-lives, that percentage of the sample will remain as the parent isotope and the rest will be the daughter isotope. So the step 2 is to now plug this value in to our equation. So you can write this one of 2 ways. So here I have the amount remaining equals 2 milligrams times 1/2 to the third, which is this value, which is little t divided by big T. Or you can also write it like this, equals 2 milligrams times 1/2 to the third. Either way, it's the same thing. No matter what equation you use, the amount remaining is going to equal 0.25 milligrams. So these units carry down into your answer because we're looking for a quantity here. So how much of a 2 milligram sample will remain after 3 half-lives or 133.5 days? Only 0.25 milligrams of the sample. That's why we can use radioactive substances and inject them into human bodies, because they have such a quick half-life that the unstable radioisotope decays quickly and basically becomes innocuous in your body.